Okay, thanks everybody for joining us for another of our Siemens webinars. Today we're going to get an opportunity to explore ShopTurn from the ID part programming perspective. Historically, we've done a lot of stuff just in more traditional OD type geometry, so we're going to take a look at the ID side of the world a bit. As always, your presenter, Chris Pollack, Dealer Support Specialist for the East Coast. Here's my contact information. Certainly, by all means, feel free to reach out to me anytime you guys have a need, even if you're certainly outside of my territory. It's quite amazing to me now that I've been doing these webinars for a little while, how many people reach out to me from actually all over the world. Certainly, email is always the best scenario, especially for those of us in different time zones. But please feel free if there's any questions, anything I can help you with, I'll try to do my best. Okay, so coming up, we have a few more webinars here. We have next one I'm pretty excited about is talking about what we call automatic calculations. Some other controls might refer to it as trig help functionality. But basically, our control has the ability of me being able to leave data out and just start plugging in info, and it will actually do the math for me. If things will start to line up, it'll compute, and if it's a possible scenario, it'll actually create the tangent points and the arcs and all that kind of good stuff. So we're going to get a chance to explore a typical mill job where we had a wonderful draftsman that left a bunch of information out, and we're going to write a program for it. After that, you're going to get a chance to see the new Mastercam 3-axis post that we here at Siemens developed in conjunction with Mastercam. They did the development of it, and what we did was we supported Mastercam. Mastercam is starting to get into doing what we call certified posts, where corporately they're going to start to build some standard posts, embed them in their software. They used to do it years back, and they kind of got out of that for a little while. So in their latest version, which I believe they're calling 2017, you will now find a 3-axis Siemens post that has been certified by Mastercam. So what we're going to do in that webinar is we're going to show it. We're actually going to bring up Mastercam and show you all the kind of cool features that we were able to embed within Mastercam to really start to take advantage of the Siemens control, even when programming it externally. And then after that, in December, we're going to be going through, similar to the program or the standard cycles webinar I did, I think it was last time or a couple times ago. But now we're going to start to look at the same context, but from a G-code standpoint, as opposed to shop mill. For those of us in the CAD/CAM world, that comes pretty handy, because a lot of times we want to be able to call some of these standard cycles from the G-code side, and it's maybe a little more difficult to understand the mechanism of them. So we'll get a chance to look at that. So certainly we're just pointing out the webinar page here on CNC4U. Here's our two main links. I would keep an eye on CNC4U. We are in the midst of rolling out a new update to CNC4U, so it's getting a complete facelift. It looks gorgeous. We haven't released it yet. It should be coming out momentarily. I think we want it out before IMTS. So certainly it should be out probably within the next week or two, is from what I believe. But same website, same address, same location, just a lot of new stuff, and just cleaned up the interface, made it a little easier to browse through. Additionally, I've talked about this in the past, but please feel free to take a look at the training classes, the in-person training classes, which are instructor-led, that we offer in Elk Grove Village. It's just outside Chicago, right by the O'Hare Airport. That's our facility here in the U.S. One of them. That's kind of where our corporate headquarters is for the motion control side of the business. We offer a series of classes. One is service-based, and the other 3 are different levels of operation and programming. So these are free of charge. There's a lot of content, a lot of hands-on, definitely well worth taking advantage of. So for those of us that maybe haven't utilized it yet or weren't aware, by all means, go to the website and take a look at it. It's some great content. I actually go out and host the 5-axis class myself. And then we have some really good instructors that host the other ones. So today we'll be talking about our 828 and our 840. So anything we talk about it pretty much will apply to either or control platform. So we'll be able to kind of switch between the two because there are very, very similar interfaces. So this was the little blurb or the little bio that we sent out, talking about what we're going to be doing today. And really the key here is to start to point out some of the things that you want to watch out for in ID turning. There's a few characteristics that you really have to pay attention of that aren't issues, certainly when we're doing OD. So we're going to explore those scenarios. We will be doing two separate parts. First part, I wanted to get a chance to start to use just some of our standard cycles. This case, we're going to treat this as if we had a part that was handed to us already with a hole in it. So, whether it's, I drilled a hole with a manual tailstock, and now I want to come in and bore and groove and thread, or the blanks were pre-prepped somewhere else, whether they were purchased with a hole in it, or a primary operation was done plugging the hole in it. But certainly this would be the first scenario we would want to look at, and it's quite common. Now, after that, the next thing we want to explore is irregular shapes, irregular contours, instead of a standard contour. So this will use our contour turning cycles. And then, how do we use a blank that's solid? So we're going to get an opportunity to drill a hole, talk about the drilling cycles, apply it, play around with it from that function. So we're going to have the two parts we're going to go through today. Certainly, though, the first thing we're going to want to do is take a look at tool creation, and then how do I set up my tools for ID operations. There are a few different things that the process has to change slightly from traditionally doing our OD or our face tools. So first things first, what constitutes an ID tool? So basically, it would be a tool that is designed to point in the inverse direction of an OD tool. So as we start to see here in the center screenshot, we have P2 or P3, as well P1 or P4 for doing kind of a back turning scenario. But in both cases, this would be an ID orientation tool. Now, certainly there's two different machine configurations in the market. We have front turret or rear turret as a standard, certainly as a standard configuration. So you will have to pay attention when you're describing the tool orientation to us from the control standpoint, where your actual turret location is. Now, what's nice within our control is we update the orientation. So if you take a look on the right side, we're showing you a roughing tool, and we have this first position. If you kind of see where my cursor is circulating around, the first position is always going to denote an OD tool. So when I say always, I'm talking about this would be a standard fixed turret type of scenario. When you get to B-axis machines, things can get a little bit different, so keep that in mind. But in a traditional fixed turret type of lathe, front or rear turret, the first position right here is always going to denote an OD tool. Now, the picture may change. So the picture I have right here is representing a machine with a rear turret. If I have a machine commissioned for a front turret, the picture would actually look like it looks in the third place over, right here. But it's always going to be the first position. So don't get too hung up on the picture. I mean, it's going to look like your real machine does. The bigger thing to denote is if the first position is always an OD tool, then the third position always going to represent an ID tool. So when we start building tools, we're going to be picking this third position. And certainly with ID, just like with OD, there's neutral tools, left-hand tools, right-hand tools. That's very typical to what we would see. Now, when you start to look at the IC standard of boring bars, there's a lot of information here. What they're going to give you is they're going to give you the bar diameter, the geometry of the bar, clamping, whatnot. Now, when it comes to that tool holder data, you'll notice down in our lower segment, we don't have any variables that we're tracking anything about the bar. We are tracking the insert geometry. So it's very, very important when you get to ID work that you pay attention to the bar size. And there's one critical variable that's not typically shown in the standard IC, but it's what's called your minimum bore diameter. So really what that is saying, if I look at this picture in the detail 3, what size hole can this fit without the back side of the tool physically hitting the back? That would be your minimum bore diameter. That is a very critical parameter to know. It is not compensated from the control standpoint, so you need to compensate for it when you start to write your parts and methodize your physical parts. Then from there, obviously in boring, we still have a lot of different orientations and configurations of the tool and how the tool physically sits in the holder. So that still relates to our orientation angle, which we have here. It's our 95 degrees. So the same way we would traditionally build a tool from the OD side, you're going to build it the same way here, defining the orientation angle and whatnot to build the tool. And we'll get a chance to build the tool in a second, so you guys will get a chance to see that. Now, when we get to drilling, there's certainly two different types of drills that would be the most standard types of drills. You get twist drills, right, with some type of an angular point, 118, 130, 140, you know. And then we have a insert style flat bottom drill. Now, what is nice with the insert drills is there's a couple of tricks that you can use. First, you don't have to drill everything on center. So although the tool may have been designed to drill a 1-inch hole, there's actually an allowable range where you can offset this tool to make the hole bigger and drill it from solid. So it's not a case where I have to drill it and then come back in. And our cycle supports that. So we'll look at that here when we get to doing some drilling. The other scenario that I might use an insert drill for over a twist drill would be for ID turning. So in place of a boring bar, these insert drills are very, very stout, and they have a tendency to bore quite well. So here is a case where I might want to use our multiple cutting edge function. So for every tool, I can build up to 9 offsets. And those what are these are D numbers here. So D1, D2, D3, so on and so forth. So in this case, we can establish a 0 dead center of the drill, and then we can establish a leading edge 0. And we can just bounce between these two offsets how I'm applying the drill. So I can use it in 2 fashions. And I can even change the type. So instead of it thinking that I'm trying to bore with a drill, I can change it to an ID boring bar in my type. It's still the same tool. It has to have the same name because it's being called up the same. It's in the same physical location. But we're going to be able to apply the tool very differently. Now, once the tools get built, we're certainly going to have to touch them off and set them up. And there are a few things that you have to think about when dealing with boring bars that you don't have to think about with a turning tool. And I'd say the biggest scenario is the fact that we need to be able to touch the ID of a surface. You know, if I'm doing a manual touch-off and not a presetter, if I'm doing a physical manual touch-off, I need to have a hole in my part to be able to turn a little ID and measure it. So, you know, it's pretty common that you're going to have either a setup piece that you're going to bolt into the machine to take a light cut and qualify the tool. Or maybe you're going to have to drill a little bit so you have some type of hole in it once you've qualified the drill, and then set the boring bar up. So those are just some extra steps you kind of have to think about. And as we build some tools, I'll show you how it does update the screen to show you that, you know, the operation would be different, like you see here in our display. Now, when we get to drills, drills get a little bit trickier. And the reason being is our system itself is designed to automatically compensate for the radius of your tool. So when I'm setting up a drill, you can see in the lower right-hand corner, it's asking me to take the tool and touch it off to the side of the workpiece. So let's say, for argument's sake, the workpiece was a 2-inch diameter. Well, and I got a 1-inch diameter tool. I come over, I touch it off, and I go to set it. It's going to automatically shift that 0 to center line of the tool, compensating for the radius. So the problem is, and when I'm setting up a tool, I don't normally touch off to the side. If I'm setting up a lathe, I'm typically going to sweep the physical holder. So like if you look in this next image, here would be a nice little example of how I would generally set up a drill. I would place the drill dead center of center line of the spindle. My mag base is on the spindle, and I'm rotating my indicator or my coax or whatever I'm using, and I find in the middle of the tool. Well, if you have the diameter already set up for the drill, and you say set X to set length 0, you're going to see it's going to shift it. It's going to shift it using that radius value. So certainly that's an undesired response that we don't want. We want it to establish everything as 0. So what you need to do is you need to make sure that we don't have that tool physically set yet. Once we've set up the tool offset, then you can go back in and add the diameter. So we're going to get a chance to see that here right now. Okay, So with that being said, as we normally do, we're going to jump over to CineTrain, and we're going to get an opportunity to build a few tools, and then just kind of talk about this setup process, because certainly this is an important process to get through. Okay, so we come into CineTrain. We're going to jump over to our offset table. This machine is commissioned as a rear turret. So we're going to build a tool. So let's build a boring bar first, so you can kind of see how the whole thing builds. So we're just going to go down to a blank spot. We're going to get the new tool option, select new tool. So now I can build a boring bar. It's going to be exactly the same way as if I was building an OD turning tool. So my two most common tool configurations would be either the roughing tool or the finishing tool scenario right here. From there, remember how I said the first position was always OD? And the third is always ID. So if I'm building an ID turning tool for this machine, I'm going to be using this third position for a standard tool that's going to run from the tailstock to the chuck. If I need to back turn, meaning I'm turning from the chuck to the tailstock, then I would use this next position. Yes, we could use neutral as well if I expand over and get to my neutral orientations. But we're using a handed tool, so I'm going to use this first one. Now, can I build it as a finished tool and use it for roughing? Absolutely. Really, it's just the picture that is the denoting finishing or roughing. It's just kind of for your own acknowledgement that you have two different operations here. As far as what the tool's allowed to do, you can interchange these all day long. So I'm going to pick mine as the finishing tool shape. We have the auto naming turned on. I'm not going to use it right now. I'm going to say that we're going to use a DNMG. Oops, I like to have caps on. You don't need them. So let's say that this was a DNMG 332, and this is an ID tool, because certainly the DNMG could exist OD or ID. So we give it some name, something that we like, that makes sense to us. We have a length X, length Z. That's gets set up when we actually do our set length. We give it our radius. So I have a number 2 radius. So we're going to have an 0.315 nose radius. And now we have our relief angle. So since it's an ID tool, I don't have to spin everything around. Everything bases off of my 0, and now it's looking at it from the other direction. So the same rules apply. If I have a 90-degree value, it's going to stand the tool straight up, so as if it has no relief. Now, as I increase it, if I have 5 degrees, I can add 5 degrees to it. You see how the insert picture starts to tip. Let's make it a little more dramatic. See how the tool starts to rotate. Same scenario, if I go less than 90, it rotates the other direction. So it's the same concept as the OD tool. It's going to automatically be inverse. So you don't have to change your numbers at all. If I look at my catalog, or I go back to that image and it shows me I got a 5-degree relief, I can just add it to the 90, and there's our orientation. We have our insert angle. We're going to use a 55-degree, and my IC. Now the IC, let's say I'm using like a 3/8 IC. It only shows a couple places here. There's not a lot of room. So it'll round it up to 0.4, but it's actually really building it with 0.375. So I like to type the full value. This is more of the picture. I mean, yes, I guess in theory you could say that I can see the back side of the insert when boring. The problem is you got a boring bar that's even further out than that. So it's not really helping you too much here. I mean, I guess you could put a bigger IC to try to track the back of it, but I wouldn't necessarily go that route. Certainly we're in ShopTurn, so we need to denote the direction that the spindle is going to run in. And if I was flipping something over, doing an inverse, then I can change my direction here and then my flood coolant. So that's pretty standard. Now, let's say we're going to go and we're going to build a drill. Maybe we'll build an insert drill or something else. So here, I have one pre-created. I have a 3/4 inch drill built here. So there you can see we have a radius and a tip angle. This would be a very typical drill. Now these drills come up when I hit new. I have my twist drill option. But if you want to get something a little more elaborate, if you go to drill, we have a few more drilling scenarios. And we have this solid drill. And the solid drill is really supposed to kind of represent an insert drill. So the drill orientation you're going to pick when building a drill is going to be pointing the direction the drill is physically pointing. So in this case, we want pointing to the left because that's where our main spindle is. Why do we have these other drill orientations? Well, that would be for live tooling, for argument's sake, and different orientations. So the next one over would be for what we call peripheral or OD drilling. So I'm drilling on the side of my part. The other direction would usually for machines that maybe have a main spindle, subspindle, and I'm drilling on the other side. That's certainly a way it could be denoted. I do have an inverse. Maybe I have a little right angle head and I'm tucking up inside of a bore. You can build a drill for that. But certainly 95% of the time, maybe even higher, I'm just going to use this first position. Now, nothing here is denoting whether this is a static drill, so meaning it doesn't spin because you're spinning the part with the main spindle, or a live tool, meaning the spindle would be held rigid, and then I could drill off-center for like bolt hole patterns, face patterns. So I have to, in this case, use the same drill for both operations. Now, what will happen a little later here is you're going to define a direction, and that's where you kind of have to pay attention to how the machine was set up and what's going on. So first of all, let's say this is going to be a 1-inch tool. We'll give it a 1-inch tool. You notice it doesn't give me a tip angle now, where I had a tip angle up top. That's because this is a flat bottom style insert drill. But what I'm talking about as far as the static or the live, if you think about the direction from the spindle scenario, it's opposite of the main spindle. So it's very common to find that you have to change your spindle direction here. Now, I've seen some builders where on a standard lathe, you always have to invert the static drills. I've seen other builders where they have this set up so it matches the main, but you have to flip the direction if you have live tools. So the big takeaway here is there can be some variance when you get to drilling when it comes to direction. The first thing I always recommend is certainly let's build a tool. Let's pick one of the two directions. Let's fire it up, and let's see if in fact things are spinning properly for this drill. If not, just flip to the other direction. There's a lot going on here as far as what's the main, live tool, non-live tool. So you always have to play this game a little bit. It's pretty common. Okay, so we've built up our drill. We can tell if we want flood coolant, if we want. Now, once we've built the drills and the boring bars, now it would be time to physically qualify them. So if we come out, and let's say for argument's sake, I'm going to start with a standard tool here. So do I have a tool? All right, so this would be a traditional OD tool, just to give you something to show. So as we've covered in earlier scenarios, as I look at my graphics, it's going to show me the tool coming down from the top, how I would be traditionally touching the tool off. Now, let's go grab that same tool, but we're going to go grab an ID tool. So the tool we just built, right, there it is. Let's load it into our spindle. So from here, now when I jump over to the measure tool, and I'm going to use manual, now you see we automatically update the graphics describing this, knowing that it's now an ID orientation. So in X, I need to get to the inside, some inside bore, and qualify this cutting edge. So this is what I was talking about earlier. So we're certainly going to need a part that already has a hole in it. So our two options, either give it something with a hole in it or drill a hole and then bring the bar in. But from then on out, it's the same thing as an OD tool. Take a nice little light cut, pull her straight back, don't move the X, measure it, type in the diameter. So let's say we took a little cut and found it was a 2-inch diameter, set length. It's going to automatically update the offset table. And if I look in the offset, now I have some calculated offset from machine 0. Now these could certainly be a distance from a gauge line. It's very, very common in lathes, especially slant beds, that things are built relative to the turret faceplate. So in that case, you potentially could see some very small values here. But then I would have to shift things with my work coordinate system. So there's two real methods of setting up lathes. Do I want to have everything established from machine 0 for my tool lengths? And there'll be large values, positive or negative, it depends on where the machine 0 is. Or do I want to set things up from some kind of a gauge line. If I have modular tooling, it's much more proficient, obviously, to set things up from a gauge line. Then in that case, I'd have these small lengths, and then I have to find where the physical part is by using my work coordinate system. Okay. Now, let's start to talk about the drill, because I do want to kind of go through this process, this step. So if we select the drill, and we can select the three-corners drill for argument's sake, it doesn't really matter which one we use. Both are going to respond the same way. You'll notice when I go to the measure tool, on the X, it's asking me again to bump the side of this tool. And this would be the same thing with like an end mill for a live tool or whatnot. So yeah, I can come in and I can set my length. So let's say I set my length to 2 inch. And you see how it's saying, oh, well, you're really 275 away, because it's taking in this diameter into account. So that's fine if I'm bumping the side of the tool. But again, if I want to bring her down and have everything lined up with center, so maybe I was expecting to put 0 in, because everything's indicated, everything's perfectly lined up, my tool's sitting down here on center line. You see, it still tells me, no, you're 750 away. We're compensating for this diameter of the tool. So what you're going to do is 0 out the diameter. You don't have to call up the tool. We reload offsets on the fly immediately. But now when I hit the set length, you notice how the display goes to 0. It's not doing the calculation. From here, once I set the tool, I can immediately go back in, plug in the diameter. It's not going to move anything. There's no cutter comp being applied here. It's just a quick calculation during a setup function. So the big takeaway, if you're using coax indicators or you're sweeping the OD of a drill or the ID of a bore, make sure whatever tool is selected, you do not have a diameter in when setting this to 0. Or the other way would be to follow the process and touch off to the side. A lot of times when I get to live tool machines, guys tend to always have a hard time getting their head around how to set up a live tool machine. So I usually will say, just do it this way first. Once you get it set up and it's cutting accurate parts, then you can go in and you play around with sweeping the inside. Okay, so we're going to jump back to our presentation, because from here, we're not going to apply these tools. We're going to start to use these in a real-world example. So like I mentioned earlier, when we first started, we're going to do 2 different programs. The first one we're going to use are just our standard cycles. So here we're going to get a chance to come in. Now this part is intentionally already has a hole in it, because it's one of the 2 scenarios you're going to run into. So we're going to just turn the inside. So we're going to go from a 1 inch diameter out to a 2 inch diameter. Once we've done that, we're going to take a grooving tool, probably build one real quick to go through the process for you guys. And then we're going to take an ID threading tool and thread the internal of it. So what that'll entail, certainly we're going to go into Program Manager. We're going to start a new program. As always, we have our 2 different conventions. So we are going to be doing ShopTurn for conversational programming. I will be backing this up sometime in the not-so-distant future with a similar webinar based on G-code, just so you can always see the difference. Then we're going to go in and we're going to start with our first header. Now this is when things start to change a little bit, because now we're going to start to use some of the options that allow us to define that this part has a hole in it already. So we're going to use the pipe option. And what you'll notice once we do it, there's going to be a new retract value that we're going to have to use, and that's the retract of the tool when doing internal. We don't want to use the same retract as potentially as OD, because OD, there's a lot more room for me to back up. So a lot of times I have to do a much tighter retract when I'm internal. So you're going to get a chance to see how that starts to get set up. And certainly we're going to start to build our program. In this case, we're going to use the standard cycles for the first one. So we're going to get a chance to use our stock removal and our groove. But you're going to see how through the one icon, I can totally change what the orientation of this cycle is. So we can flip it from an OD to an ID, fill out the appropriate geometry, cut that feature. We'll do the same thing for grooving. Once we have the grooving done, then we're going to go back and we're going to take a look at threads. And we're going to build a physical ID thread. And then once we do everything, certainly we'll get a chance to use our simulation. Now when we get to ID, if you keep it whole and we're looking at it from the side, you're going to notice you don't see anything inside the part. So there's a nice sectional view that we'll use, a half-cut view, that we'll use to be able to see the internal while it's in process, while it's machining. So we'll do that. I'll show you how to get to that. The other common thing that we do in a 3D orientation would be to use the cut functionality and cut away the solid so I can start to see some of the detail on the inside. So we'll touch upon that as well and show you how to use that type of functionality. Okay, so within ShopTurn, I do want to bring up, just so you guys have it, the drawing here. Just kind of keep it in the back of your head so as I'm plugging in numbers, it can kind of make a little more sense to you. So if we look at the job, we do have a through hole of 1 inch diameter. We're going to have a bore of 2 inch that goes back 1.5 inches, and the stock or the rough part is going to be a 3 inch bar. I'm going to assume that this has already been maybe cut to length, so I don't have to do any facing. So we're just going to come in with a boring bar. We will generate this chamfer here in the face. We're going to put a nice chamfer in the back section as well. And then once we're done with that, we got to put in a little thread relief here. We're going to do a grooving cycle. So we got some dimensions here. We do a 250 wide groove, an 1/8 inch deep. Once we get it all grooved out, turns, we can go back and put a thread. We'll put the ID threading cycle in. Okay. So just like building any other program, we're just going to want to start by going to Program Manager. We want to pick where within our memory we want to create a program. Certainly I could be building programs in our NC, our local drive, which would be an extended memory if you happen to have it. Build them on USB, build them on maybe an external network or whatnot. We're just going to work in the standard part program memory. Select New. Let's give it a name. Now, remember, we're doing ShopTurn, so we got to make sure we pick the appropriate radio button. It will remember this. So if I always do ShopTurn programs, I don't have to pick it every time, just this first time. Now let's give it a name. So I'm going to call this example _1. So we type in the name. Letters, numbers, underscores, nothing else. We don't have to put the extension. It'll automatically assign a .mpf, main program file is what it stands for. So the standard extension. Say OK. We're in creating the program. OK. Now, commonly in lathes, especially new users on simple lathes, they don't typically use work coordinates. So I got a couple options here. I can leave the work coordinate selected, whatever one I want to use, but I got to make sure that there's no numbers there, because it will apply. I could tell it blank. The only downfall of blank is if I leave a work coordinate set up on the machine externally, meaning in the jog screen, and there's a value there. When I run this program, it's going to use that because that's an active offset. Or I could use what we call our base reference, which is also G500, and that would at least cancel any work coordinates that maybe were left in the system. At some point, you're probably going to want to start to use work coordinates. So I typically have guys start using G54 and just making sure they leave it blank initially until they start to understand how it applies. Describe. Describe is used more for production-oriented operations where I want to write the work offset from the part program. So be very careful with this option. I would say typically always set it to no. But, you know, let's say I'm running a job and I'm worried about an operator overriding an offset. Or I just have a fixed offset that I know that I don't want to potentially get changed. I can let the part program physically write. So it'll literally write whatever value is in here to the z-axis field of the work offset. So that's why we're going to keep it at no. Now, when I'm defining the blank, typically we always use cylinder. But once I have something with a hole in it, well, I need to tell it there's a hole in it, or it's going to think I'm crashing into my part. So we're going to select the option pipe. Now, once I'm building it, now we're going to build the physical blank. So the 3-inch, that would be the OD of the blank, OD of my bar. Now I have two ways to describe the ID of the hole. I can describe the diameter, that would be the diameter of the through hole. Or if I hit the select key, I can change it to an incremental value, and now it becomes the wall thickness. So for pipe, I quite commonly know the wall thickness, maybe over even knowing what the inside bore is. So it's pretty handy to be able to toggle it to here. But a lot of cases, if it's something maybe I drilled through a previous operation, I know what drill I sent through it. So then I'm going to want to toggle it to absolute and then define that value. From here, I can denote where the start plane is of the stock. I'm going to use the front of my part to be 0. Anything negative is in, anything positive is away. Then we'll give it the overall blank, and this is very similar to what we've done in the other parts. And then my stick out from my jaws. Now, it's very common in ID that this value can become a lot less. I can throat this part pretty heavily, especially if I'm not doing any turning operations, because the machine can bore past that. I can send my tools past that. So for argument's sake, let's say I did this job, and I only gave it 1 inch for this distance. So you'll see when we get the simulation how it'll let it go past that. That's okay. Now, once I select pipe, I automatically got this retract field up. So if I'm on cylinder, and this is that simple, see how it's blank? We pick pipe. Now the retract value comes up. So I don't have to toggle the retract strategy. Now I can, if I want to get all of them, but I can just keep it that simple with pipe. And now I know, now I got to give it my retract. So my OD retracts can stay the same as we've been using. But my ID retract, now I have 2 options. I can certainly use an incremental value, but an incremental value I have to kind of keep track of all of my data positions and kind of how they stack. Well, if I change it to an absolute, now I can give it a true known absolute diameter, and this is where that minimum bore size comes in of the boring bar. So what I like to do is I like to find out what the minimum potential boring, bore diameter that bar can go into, and I'll use something just slightly bigger at as long as I have it. So in this case, I'm assuming that the boring bar we chose can bore through a 0.7 diameter hole, can fit in a 0.7 diameter hole. So that's what we're going to do. Then I have my Z retract. We'll just use an incremental. Where am I tool changing? And this all stays the same. Safety distance stays the same as we've used it in the past. And if I had live tooling, I could denote climb milling or conventional mill. Okay, so we accept our event as we normally would. Now we're going to jump over to turning, because here we're going to start to put in some geometry, give it some operations. So the first thing I want to do is I'm going to do a stock removal. That's going to let me clear out all this material. Now there's 3 stock removals. What we're going to use is the second one down, because the second one down allows me to put chamfers and radiuses in my corners right here. Okay. From there, we're going to fill out the cycle like we normally would. So I want to come in, I want to pick the ID tool that I selected. Now I can go right to turning, because remember, this part already has a hole in it. We give it some feed and some speeds, constant surface speed, RPM. All this is going to stay the same as we've seen in other webinars. Really, the big thing that's going to change, and we still have roughing and finishing, all this is the same. The big thing that's going to change is the orientation. So you have 4 different orientations you can use for this cycle. The second one down is representing an ID, standard ID turning orientation on the main spindle. We also have another ID, which could be either denoted for back turning or subspindle, but typically this would be more of a back turning type of scenario. So we're going to pick a standard ID. Now, even an ID, I can turn or face, doesn't matter. And then we start to fill out our movement. So our starting diameter, before we're used to working from the outside coming in, now it's opposite. So I'm probably going to give it what my hole size is. So in this case, it's 1 inch. Where is the face of the part? It happens to be 0. Where am I ending? So I'm ending at a 2-inch diameter, or potentially if I actually knew what the true thread diameter would be, it would be something slightly less, but that's fine. We'll use 2-inch for now. How far back am I going? So look at the print, it's 1.5 inches. And now we can use, and we can toggle with the select key. All 4 corners can be toggled from radiuses or chamfers. So FS is going to denote a chamfer. Radius is going to denote a radius. R is going to denote a radius. So you come in, set it to your chamfer, give it a value. So if you look at our print, we got 0.75. So that's our 0.75 there. We have our back radius. Then I have another chamfer. This is going to be the inside chamfer. We have another 0.75. We have a depth of cut. So maybe we'll take 75 thou, oops, per pass. Sorry, guys. I have to start over. All right, where was I? Select the tool, 0.75. We're going to do a 0.075. I got my number locks off. Danny is laughing at me right now. Okay. So what happens with CineTrain is I turn the number locks button off to be able to use the select key. And if I forget to turn it back on, it actually switches pages on me. Sorry about that. All right, so we're going to use an 0.75 depth per pass. Do I want to leave material for a finished cut? Certainly I could if I wanted to, but we'll just bring it right to size for simplicity's sake. So we save it, and now we have really enough geometry to start seeing what's about to happen on the inside of this bore. So we can go to simulation. Now, you see how I'm throwing it in, but I can't see anything. I can't see any motion. Well, that's because I'm going to want to go to further views and use our half cut view. So we select half cut. Everything gets sectioned. So now I can still run it. I can have left it in half cut, and I'll see the tool come in, start machining out the part. So you see this kind of faint gray area? That's our jaws. So the machine's going to let you blow past the jaws. It understands in an ID operation. It's not, the jaws are here just for a representation for you. It'll let it go by it, as you see right here. Okay, so we have the shape. It's turned. We have our two chamfers. It's looking good. So now let's go back and edit our part program. Next thing I would logically want to do is probably put the thread relief in. So we're going to go to grooving, and now we're going to fill out this page. So first things first, we wanted to build a tool. We didn't build one before. So I'm going to create a new tool. Now when I'm doing a grooving or a part-off tool, it's going to be a plunge cutter. So the first orientation, if I think about this being a slant bed, a rear turret, these first two orientations are OD. These next two orientations are face. So here I have to expand over to get to my ID. And these next two right here are going to signify an ID grooving tool. Now when doing grooving tools, there's this little kind of indicators, two little lines at the corner. That's telling you where you're qualifying the tool from. So do I want to work off the leading edge of the tool, or do I want to work off the back edge of the tool? We're still going to get the width of the tool, but now we're going to know which direction to apply the width in. It's really what it comes down to. So normally you would work off the leading edge, but you don't always have to. So I'm going to pick this first one with the little indicator to our left. So we're going to say that this is a plunge cutter. Sure, we'll leave the default name. And it's a 250 groove, so maybe this is going to be a 125 wide plunge cutter. And I'll call it an ID. Oops. My caps. Now, if the name doesn't fit in your display, it still will work. I believe we support, it's quite a few, 24 characters, I think, in a name. I try to keep it, I think the 16 is pretty common, that'll fit. But you can get pretty big on the names of the tools. Okay. We are going to ask for the corner radius of the tool because I can come in and do a little profiling or finish pass with this tool. So let's say, for argument's sake, I happen to know I had a 5 thou corner break. What is the physical insert width? This is important. So this is that 125 or that 1/8 inch wide we just mentioned. The length of the insert is just for the picture. If I give it a length and it's grooving deeper than the length, it'll let it go. It's just the insert length. The holders themselves can project those inserts way out. Then certainly everything else would normally stay the same. Okay, so we build up the groove tool. We're in. We give it traditionally a feed rate and our spindle speed. Now we can do roughing, finishing, roughing and finishing. Let's say maybe we're going to try to do a rough and finish with the same tool. That's fine. And then I'm going to use this picture to orientate the groove. So it can be OD, it can be face. For us, it's going to be ID. The next indicator controls dimensionally where I know the groove information from. So this is going to relate to our print. So if I look at the dimensions, I was dimensioned from the face to the back edge. And then my width came off that. So it's only logical for me to use the point that's on the lower left side. Now, I could use the point that's lower left side, but in the deepest part of the groove, especially if I had a taper to it, that becomes critical. I could use the other side, the right side, on either side of the groove position. So we're going to use the lower left corner, and now you're going to give it some basic geometry. Now you notice the value is actually already here because I already got a chance to program this part earlier. So we always maintain the last entries that were put in, so just streams up, saves a little time. So we have the physical starting position of the bore, which is 2-inch, set here. Now, since I'm using this indicator, I'm using the back edge, which is my minus 1.5 to denote. We have a groove width. Groove width 250, so I plug it here. We have our depth of our groove. And the depth of the groove, see how you got the incremental notation? This could be toggled with select to absolute or incremental. Absolute would be a true diameter of the groove depth. Incremental would be the physical depth from the start point to the bottom. So in this case, I know it's 125. I plug in 125. Now, I don't have to give a plus or a minus here. This is an unsigned value because the orientation tells us what direction we're moving in, not the dimensional data. My PEC amount. Do I want to leave a little material for a finish? Yeah, I said we were going to let it do a finish cycle. And then do you have multiple grooves? So, if I tell it, yeah, I got some grooves, I can define the distance between each groove. But in our case, we only have one, so that field goes away. So you'll see that dynamically, these screens will change based on the inputs you give it. Fill out the page. We hit accept. Grooving cycles there. We can simulate it real fast, and you get to see the groove come into play. So now we're turning, as we saw. Tool comes in, builds it. Now, I could have used a slightly different grooving cycle if I wanted to do a corner break on this edge. So back here in groove, if I use this grooving cycle, now I can do corner breaks on all my 4 corners. So I could just pick one of the 4 corners had I wanted to, maybe put a nice chamfer for that thread. But we just use a standard square groove for now. Okay, now it's time to go in and put an ID thread. So we're going to go to our threading cycle. Now, I have pre-created the threading tool, but I do want to show you something. This is a little trick. Okay, so here's our thread. Pretty standard. We're going to build the same way an OD thread would. You see the insert length right here? See, I have this giant number of 10. Well, on some versions of software, we weren't converting this number properly when it came to simulation. So what would happen is we were looking at the number and treating it as a metric value, even though I'm in an inch mode. So if I left this and put a more appropriate value of like 0.5, you're going to see this tiny little insert's going to come in. So if you happen to notice that on your machine or your CineTrain, it's just I don't even want to use the word bug, but it was an oversight on the way we were formatting the numbers. So put a metric equivalent value. So if you wanted to, what's it, 12.4 would be ½ inch. Plug that right here, and then it's going to display it as a ½ inch tool. So I had just thrown a 10 in here to have something. But you'll see we can change it. Now we're going to build a thread. And the thread's going to work as it normally would. We do have a table if we want to use the table. If not, I can come down to our field here, in this case to the right of the P, and I can select basically 4 different types of thread, or 4 different ways we can describe the thread. So a module thread, I can describe the pitch in metric, I can describe the pitch in inch, or I can describe the pitch in threads per inch. Now, what's important here to keep track of, and later it comes into play, is the thread height. Unfortunately, we don't auto-calculate in inch threads. So if you watch, see how I have a value of 450 here. If I type in a value of 10, my thread height didn't change. Right? Thread height is the depth. But we do auto-calculate in metric. So I'm going to just to show you, zero this out. And this is a little trick I do when I want to be lazy and don't want to look up the thread depth of a thread. plug in thread value in inch, whether it's threads per inch or pitch, and the system will automatically convert this to a metric value. So it converted to 2.117. If you type that value back in, watch what happens to the H1 field. Oops. And I just did the same thing I did before. Darn it. All right. Get me back to where I was. Fat fingering stuff today. Okay. Catch back up. All right. So we were going to plug this number back in. But we're going to plug it back in as a metric number. So I'm going to type in 2.117. See how it calculated the 451? Now, I can switch it back to inch. I can leave it here. It doesn't matter. It already did the math for me. So if you are using our threading system with OD or ID, it doesn't make any difference. If you want to auto-calculate, you do have to plug in the physical pitch in a metric value. Okay. Some RPM. What's my strategy? Roughing or finishing. This is all the same as we've done in other operations before. Linear or degressive. Constant depth, constant volume, right? So typically I would always want to use a degressive value, so the depth of cut would reduce as I get deeper in my engagement. But this is what controls OD or ID. So is it external or internal? Now when you're dealing with internal, this becomes the true minor diameter of the thread. So really a 2-inch thread wouldn't be 2. It would be something a little less because 2 would be the OD. This is just a quick example, so we're going to leave round numbers. So we'll leave it at 2. But whatever your bore diameter is, whatever you bored it out to, that would be the position generally that you would put in there. Start of the thread, 0. End of the thread, where am I going to end? And I'm going to set mine to absolute. My thread advance or my overrun, typically I like to keep about a thread pitch here if you have the room for it. It's good practice. My overrun, so if you set it to 0, she's going to maintain the minor as close to the end as it can, and it's going to rapid the tool out. So you may lose a quarter, half a rep, depending on how coarse the thread is. My thread height, that just now auto-calculated. My in-feed angle. Now with in-feed angle, make sure you toggle it from DP to the angle P value, because DP is going to be looking for a physical linear distance. It's much easier to just use half of the insert angle, which in this case would be 30 because I have a 60-degree insert. We have depth of cut or number of cuts. So even in aggressive, you could give it a number of cuts, and it will try to then figure out, based on those numbers, how to optimize the thread. Generally, you're going to want to have depth of cut, and then you're going to give it the first depth, and the system's going to automatically reduce those as it gets deeper into the thread because I have degressive selected. I have my finish amount. In this case, I'm going to take 1,000. I have number of spring passes or idle passes. And this is very common to use in threading because you do have a lot of force being created. So I'm going to do, my goodness, I am just having one of those days. I'm going to do 2 spring passes. Now the retract here, this is important in ID. You know, usually I don't really care about this in OD because I got a mile I can retract. But here, if I got a big stout bar, right, a huge bar, and I don't have a lot of room, well, that little retract could be too much. So remember, this retract is based off of the X0 location. So here I'm telling it, and it's a radial value. So if I'm at 2, I'm really going to go to 1.8 for my retract. So just be careful of that. Okay. Do I have multi-leads? This is the same as if it was an OD, or do I want to control the orientation of the start? So we fill out the page, we hit accept. Now we can go simulate it, and we should have a finished part. So we're always going to get our little wireframe representing the bottom of the thread, where the threading tool is going to end. Here's our grooving tool, comes in, grooves it out. Voila. And then you see the thread tool come in. So to kind of show you what I was talking about before with the physical size of the threading tool, here I get a nice picture, a nice profile thread. You know, if I turn off my show path, it really gives me a nice, good-looking thread. Well, if I had done what I would have expected to do, which was put maybe like ½ inch for my IC, and we simulate the exact same part, you're going to notice based on the version of CineTrain I'm running, it's interpreting that IC as a metric number. So turn looks good. Groove's going to look good. And now watch the thread. So you don't even see the tool. It's tiny because it's converting 0.5 millimeters into an inch value, which is obviously going to end up being very, very small. So that's the trick. We have since resolved this in later versions of software. I don't necessarily think if you have this occurring on your machine, I don't know if I would go running and changing software. That can be pretty involved. But I do want you to be aware of it because it's a pretty easy fix to just plug in something a little bit more realistic. And now when I go to run it, I'm going to get that nice picture of a thread. Threading is probably one of the more simple operations because there's not a lot of computation going on here. It's not like, my turning tool where I can dive into profiles and it'll track the backside. It's really just to kind of get a nice picture for just to denote things look like they're going to appear. Okay, now we did talk about, what if we wanted to look at this three-dimensionally? Well, it starts to get hard to see some of these features, like, maybe I want to see what the groove profile looks like. So that's where under Details, you can hit the Cut view. If you want to use Cut view, you have to hit Cut Active, and that's going to give you a sectional view. Now, use the X, Y, or Z to move the cube around. So depending on how much of the part I want to see, I can move the section of the cube. So I'm going to move it back a little bit. And then we cut it out. So now you notice as we zoom it around or whatnot, we can start to see all the detail of the relief and the thread. And the only downfall with cut is every time I move, I rotate, I refresh, I zoom, it's going to need to refresh the cut. On your PC, it's going to go pretty quick. On the machine, on some of the NCUs, there's a lot of calculation being done here in the background. That might be a little on the sluggish side. So normally, once I'm done with cut, I just always make sure I come in and take it back off. And I'll be honest, majority of the time when I'm proving out an internal part, I'm just going to want to come to my further views, half cut view, because really this is all I need. I just need a nice sectional. But if I'm doing live tooling, peripheral drilling, face drilling, milling, all those good stuff, then absolutely I want to start to look at things in 3D. And that's where the cut function becomes very, very handy. Okay, so hopefully you guys found that helpful. Now what we are going to do is we're going to kind of go to the next section, and really that comes into irregular shapes. There's two things we want to finish up with today. We want to say, well, what happens if I don't have a part with a hole in it? How do I handle that? And then how do I handle an irregular shape? Right? I don't want to just use the can cycle. So this next job, we're going to punch a hole in the part through the part program, and then we're going to bore this shape. So we're going to use some extra functions here, and we're going to use our centric drilling cycle. And centric is automatically going to position the x-axis to 0 for me. So I just give it my physical, you'll notice there's no x values, just give it my physical z positions. And since I chose centric, it's going to bring the x down to 0 and drill my hole. Once we've drilled the hole, now we're going to use the contour turning function like we normally would do on an OD, but we're going to draw things inverted because it's now an ID shape. So instead of starting usually at the smallest position and working our way out, we're going to work from the largest position and work our way smaller as far as the X is concerned. Then we'll use the actual physical contour stock removal cycle to link in and machine this shape. And we can certainly use any of the 3 strategies here under stock removal. So let's segue back to CineTrain. Let me bring up the other print so you can kind of keep an eye on some of the data here as we plug it in. And I'm going to zoom in here. Yeah, let me zoom. Yeah, there we go. Just try to get a little bit bigger on the screen for you guys so you can see it. Let me just go back just a little bit. All right. Boom, boom. So there we go. So we're going to have a little regular shaped bore. Part's going to start out, in this case, this example starting at 3.150 is the rough stock. We're going to assume that this has been pre-machined as blank. I'm not going to worry about facing it. I'm just going to come in, we're going to generate the chamfer, create the bore, create the shape, and finish up our part. So in this example, we're going to start it the same way. I'm going to use example 2 now for our new name. But I got a couple options. So when I come down to my blank, I can still use cylinder. I don't have to use pipe, and I probably don't want to use pipe because, let's face it, the part is solid. So I'm going to come down, I'm going to give it my blank size. We stated it was 3.150, front 0. Overall on this is negative 3.150, that's fine. And minus, I don't know, 1.5 is sticking out. But if I use cylinder, at some point I'm going to need this ID retract. So it's important for me to now remember I can extend this because I know later down the road I'm going to need this retract. I really have two options. I can either do this now, or there is an event I can place under various halfway through my program to change this retract strategy. I can really change just about all the strategies on this page mid-program. That would be under various. But normally what I'll do is I'm just going to use extend. Now, you got to be careful here, because if you leave this as an incremental value, the system says, hey, I understand that this only works if I have a blank of pipe. So a lot of people, if they weren't using absolute, thought they always had to cheat and put some tiny little hole, you know, like maybe I'm going to put a 10-thou hole in this pipe because I need a retract of incremental. So the big trick here to pay attention to is, as long as you're using absolute, which is really the safer method anyway for our retracts and bores, I can pick cylinder. I don't have to cheat and kind of leave hole. I can leave this as a solid object, and now I can use a true retract. Now, in our case, this is going to be drilled at a 3/4 inch hole. 700 should be okay. We could probably use the same one. That should be all right. Okay, so we've filled out the page. We're going to hit accept. Now we're going to go in and we're going to pick our drilling. We're going to drill our hole, and we're going to talk about drilling a little bit. So when I go to drilling, I'm going to see one of two things, and this really depends on how your machine is commissioned or built. So this machine that you're looking at here is designed to have live tooling. So because it's designed to have live tooling, I get a whole bunch of drilling cycles here. Same cycles, if I'm familiar with milling, that I would see on a milling machine. The problem is, I don't want to use a live tool. I want to use what we call a static tool, right? It's a non-spinning tool. I want my part to spin when I drill my hole. So what we are going to use is we're going to use our centric cycle. Now, if your machine didn't come with live tools, the centric button is still here, but the rest of these will be just gray boxes. So we will add or subtract functionality based on how your machine is built. There's no reason for you to stare at cycles that are designed for live tools if you don't have a live tool to be able to use them. So for us, for static drills, you're always going to go to drilling centric. Now, drilling centric handles two things. It handles drilling holes, but it also handles tapping holes. So instead of giving you a bunch of different cycles, we really just give you our standard pecking cycle, and then it's up to you to kind of manhandle this cycle. If you don't want to do any pecks, you just give it the depth per pass equal or greater to the depth of the hole, and it'll take it all in one shot. If you do want to use it, you can chip break or peck, really just to simplify, not having to have, try to fit all of those drilling events on that one page. Here it's time to start creating and picking our physical geometry. So first things first, I would certainly want to select my tool, and we had the 3/4 inch tool, and we do have a diameter called out on that. The diameter is really only going to give us a diameter for graphics purposes. Other than that, you're always working from the center of the drill on a centric type of scenario. So I don't need my diameter here, but I'm not going to see a drill hole if I don't have a diameter. So that's why I want to remember to plug it back in for the simulation. Now, when we're drilling, just like if we were OD drilling, I can toggle this between feet per minute or feet per rev. We can go straight RPM or constant surface speed. So I'm going to go something a little more legitimate. We can certainly do a chip breaker or chip removal cycle. So maybe I'll do a chip removal because I don't have through coolant, let's say, on this machine. Denote starting position for my stock or my material. And then how do I want to compensate for my drill? So I can use tip or shank. And then the system will compensate for how far it has to run the drill. So let's say, assume I use tip, but I left the drill depth of the length of the slug. You're going to see it's not going to drill all the way through the shape. And then we can jump over to the other one. You'll see it change. Depth per pass. So here we're going to take a 3/8 first peck depth, and then we're going to back that up by something, and we'll see what the something is in a second. Now this is pretty handy. This is our feed for our first infeed or first peck. So a lot of times when I'm first coming in, let's say if I'm using like, I don't know, 130, 140 geometry drill instead of a 118, well, I probably didn't center drill it. I'm just going to come in, but I may want to go a little slower on that first infeed. So here it's saying, hey, I want to run 50% of whatever my program feed rate is. From there, the next question is decrementing for my peck amount. So I can select a percentage or a value, and this is amount for every further infeed. So if I wanted to take the depth of cut, the D, and then start to reduce them, I can now put a percentage, and it would become 80% of whatever the last peck was, and then 80% again, 80% again. Now, once it sees that my peck value is decreasing, it does give me a minimum peck amount. Now, in this case, the system is saying, hey, your minimum peck is greater than your actual first peck, so it doesn't like that. So I would have to change this to something smaller than, so in this case, she'll start dropping the peck until it reaches 250, and then maintain a 250 peck until the end. If you don't want to decrement down, if it's not super deep hole drilling, usually you don't have to, then I would leave this at 100. My retract, if you want to control what the retract value is, you can set it to manual, or we can do a automatic, and it'll automatically back up. Now, you can control a dwell at the bottom, and sometimes this is nice to just pause the drill just for a second. One, to keep it from, maybe it'll catch a burr that would normally get pushed out. Two, it gives chances for coolant to flow through. So, here I'm going to have a 0.1 second dwell. Now, this is how we adjust for that offset for that insert drill. So remember earlier I mentioned that an insert drill, you don't have to drill right at 0. You can actually make the hole oversized to what the tool is. So that's what this XD value is. Now, it's important that if you're going to do this, you go to your insert, you go to your tooling catalog, whoever you bought the drill from, and they will give you a maximum offset value that that drill can handle, and you have to stay within that range. But here, then you would just literally put it. So, am I going to offset it 50 thou, or not half inch? That's big. 10 thou, whatever I'm doing, and it'll offset it. Now, you notice here, even 50 thou, we were limited. There is a limit in the machine parameters to control this. So if your drill can offset greater than the limit, that can be adjusted certainly in the machine parameters. So it's something you could always reach out to one of us or your OEM, and we could kind of steer you in the right direction on that parameter. Okay, so we fill out the page, we hit accept. So now if we start to simulate it, with a drilling cycle, she's automatically going to launch the cut view. So like let's say I had left it to just a standard side view and come back in to simulation. Oh, made a liar out of me. Well, maybe we don't do that anymore. I thought we did. All right. So we have our section view, our cut view, and you can see the tip Well, that was because I drilled, I told it to drill just to this edge. So if I'm working up the tip, I now have to automatically compensate for whatever this projection of the drill is. So that's where our tip shank comes in. The shank will now say, I'm going to go 3.150 plus whatever I calculated based on the diameter and the angle I know from the offset table. And now, in this case, it'll make sure it just breaks through. So we see the tool, peck, peck, peck. Let's watch this edge. Just broke through. Now I have my hole. Okay, so from here, it's time to turn the ID. So I'm going to go over to contour turn like I normally would for an irregular OD. I'm going to select new contour, give it some name. I'm going to call this my ID, shape, whatever I want to call it. Say accept, and then we're going to build it. So the difference here really is we're using an OD starting from a small diameter working to a big. Now we're going to start from a large diameter and work down. So in this case, I said that I wasn't worried about facing it, but I do want to get this chamfer of 079 in. So I'm going to start at the bore diameter, which is 2.559. 0. I'm going to tell the system that I have a chamfer leading into it of 079. Oops, 76, 79. Now you see this little picture? This has to align with the direction of motion, so the direction that the chamfer is pointing in. If you get this wrong, you're either not going to get any chamfer at all, or it's going to go the wrong way. So don't be afraid. Just pick one if you don't understand it. But generally, it's going to be your point of direction. Kind of pointing to the path I would take. If this was an OD part, I would have used the inverse. But since I'm pointing down, that's the direction I'm going to be moving for my cuts for X. I pointed down. Okay, we give our first position. Now we're going to roll around this part. So on the print, we move back minus 1.181. There's no transition, except, and this becomes the same as you guys have seen in other webinars. As far as plugging my data in, I'm just really picking the points right off the shape. So now we're going to do a 2-axis move to a 1.772 and a Z of minus 1.575. We happen to have a radius, a nice swept radius here of 0.394, big radius. Accept it. We're going to go back to the minus 2.362. Oops, not 362. I don't have any features back in this corner, right? That's my 362, so accept it. We're going to come down to my hole size, which is 0.787. We do have a little chamfer there of 0.079. Now, I drilled it with a 3/4. It's finishing at 787. So I need to get into this hole and do something. So I'm going to now pull into the hole. I'm going to go back to the minus 3.150. Now, at this point, those of us that do a lot of OD work are used to doing a pull out to the rough stock. And you can do that here. The problem is, I pull out to the rough stock, I'm now forcing the tool, even on the finish pass, to pull back and start moving the back of the boring bar towards the other side of that hole. So that can get a little tight, especially if I have a big boring bar here. Typically in an ID, I will usually end in a Z move. Now what the system will do, because that's the last geometry point, it will overcut this position by the radius of the tool. It will position the tangency of the radius of the cutter, in our case 31 thou. So be aware that if I'm stopping in Z, that the tool can move further in. Now this was just a slug. There's a hole here. There's all space, so I can let it go there. So in this scenario, I'm not going to pull off in the X. If you do pull off in the X, just be aware she's going to come down to that position even on the finish, and then back off its clearance amount or its retraction amount, and then pull out of the hole. So that's where you want to watch yourself. Okay, so we draw the shape. We hit accept. Now we're going to pick our stock removal. We go select our tool. We use the same tool we built before. Speed and feeds. 4.5, we had introduced the ability of roughing, finishing, or finishing and roughing in this cycle with the same tool. Earlier versions, we didn't have that in. So if you choose that, then what you get is you get a finishing feed option here. If you notice, if I'm just in rough, that field goes away, or just in finish, I don't get that field. I don't use it a lot in turning because I typically have the luxury of having a roughing tool and a finish tool. Boring, however, it's more common that you're only going to have one boring bar, and the boring bar is going to use to rough out and finish the geometry because I'm limited in turret positions or tool positions. So in that case, in boring, I have a higher tendency to use this feature. So here I would certainly want to drop my feed rate before it drops in to do the finish pass. I can use all the same strategies, turning, facing, contour, turning, but now I got to make sure I'm not outside, I'm inside. And this is how we know the direction of our cut, all that functionality. From there, depth of pass like I normally would use, amount of material I want to use for the automatic finish pass, if I want to do an interrupted feed. Now, cylinder is important, as it always is. This is saying I'm going to be doing some kind of box. Now, it's not using the stock to figure out where it has to machine. So the blank that we described and things that have been machined, it doesn't track that. It's using this right now. So I have 3 options to tell it what I'm machining from. I'm doing a cylinder or a bar. I'm doing an allowance. So the part's already been machined, but I just want to clear off a little more material. Or I'm drawing a shape that denotes the stock. So in our case, we're using a simple cylinder. Now, I'm going to leave my value 0, and you're going to notice that when it roughs out, it's never even going to attempt to enter in this bore. From there, we can then give it some value if we want to make sure the tool kind of comes into the bore and roughs it. So that's all controlled by this BL, the cylinder, and XD and ZD. We can do relief cuts if we had any pockets, which we don't, so I'm not worried. And then if I needed to limit the shape. So we fill out, accept it. We go to simulate. And now we see we're drilling our hole. And watch the boring bar. So you notice how it never went into this hole. So you can really start to control the motion that you're getting just by understanding those little nuances of the cycle. So you notice it finished the hole. Finish cycle is always going to run every geometry point. But the roughing, it said, hey, you're not telling me I have any additional material on X, so why should I even go into that hole? If I had a pull-off here, then it would have gone into the hole. Because it would say, okay, well, my 0 is the end of the pull-off, but now I know there's material here because I'm using the shape to gauge where my stock is. So if I need to go into the hole, now it's as simple as just giving it a little bit extra. So, let's say, for argument's sake, I said I had 25 thou, just X, all I need. Simulate it. It would be the same thing if I had started coming down the face in Z. If I said 0, it would never touch this, only for the finish cut. So now you can see, went into the hole now. So that's how I can control in scenarios like this. Everything's really tight. Why should I even send it in there in a roughing operation if there's not that much material to take off and I can handle the finish pass? Okay. So hopefully you guys found that quite helpful. So what we're going to do now is we're getting closer to time, so why don't we open up to some questions. Remember, questions can pertain to this content or any content, and we can kind of try to field them as we go. So you guys have a Q&A panel. You can use that to type in any questions, and we'll go. Does the Siemens have a way to avoid gouging the tool? Yes. So you have full insert checking and gouging active based on you creating the geometry of the tool. So, when we built this tool, we told it the relief angle, we told it our insert angle, and we told it really so it can back calculate where the backside of the insert is. So if I send this tool into an area that it can't fit, it's going to use as much as it can. But important, it's not tracking the boring bar. So that in ID, I do have to kind of watch out for. So just remember that. There was another question, arrow point to the tangent. I'm not quite sure what Danny was talking about. If you want to clarify that, that would be great. Fabio thanked me for the webinar. Thank you for attending. I appreciate it. All right. Any other questions anybody may have, feel free. I know it's summer months. It's always tough. I appreciate you guys jumping on. I think a lot of us are just trying to enjoy the summer. Okay, here's a good one. They were asking, can I use the other contour cycles when doing ID turning? And the question is absolutely yes. So what they're talking about, and I didn't get a chance to go over them, but under contour turn, we have stock removal, but we also have grooving and plunge turning. So any of these will support ID. So just look for the option inside outside. So here you see I pick inside for groove. I can groove any irregular shape. The same scenario for the plunge turn. So I come to turn and inside, and now I can plunge turn ID. The same holds true for all of our residual materials. The cut residual says, hey, I couldn't kind of fit all my material, back to the previous question of insert gouge detection. Residual material will say, well, I stayed away. Now let me take a new tool, figure out where the previous one couldn't fit, and I'll come in. That's going to work OD or ID. So really, anything you can do in any of the orientations. That's what makes the control so powerful, really. It's very adaptive to that kind of stuff. All right. Oh, Danny had mentioned that it might be a clearer way to describe the way the arrow is pointing to align to the shape. I follow you now. Okay. Oh, okay. Just another question was coming in. When we were talking about the gouging, he was wondering if it has a variable tool path. And yes, so what they're referring to, these little indicators on the side, I can control my cutter path. And one of them we have allows me to do this variable depth cutting. So what happens is one cut will be straight and the other cut will come in at an angle. And I actually covered this in detail in an advanced turning webinar. What's great about this, especially in some pretty nasty materials, you get a characteristic called insert notching. What's happening is if you're taking the same exact depth of cut every single time, there's a lot of wear occurring at the point at which the insert is just touching the material, not the tip, but back on the insert, down the flank. So if I'm taking a 100,000 depth of cut, the position where the material stops is 100 thousandths down the physical insert. Well, you will get a notch. It'll start to undermine the insert and prematurely degrade or fail the insert. This little variable now changes the tangent point on the insert as you're machining, and then it reduces the potential of insert notching. So yes, I got the question. Very good question. Okay, so we're pretty much at time. If everybody else is in good shape, I'm going to stop the recording now.